Okay, so first of all, it's a real pleasure, privilege, and honor to be here and to share some of the excitement with you about what's going on in terms of the current sort of hot developments on two problems that I worked on in astrophysics. One is trying to understand the nature of dark matter, and the other is trying to understand black holes, how they form, how they grow. And what I want to end with today is like a new result that you cannot take pictures of, okay? It's embargoed. It's a paper that's still under review in Nature, but I want to share it because it's so exciting, because bizarrely, it brings these two problems that I've been working on together in a completely unanticipated way. So first, what I want to start off is trying to give you all a sense of the history of ideas in cosmology. And as Shomak referred, I wrote a book a few years ago, and I've always been interested in how radical new ideas get accepted in science more generally, and cosmology as a case study, because so much has happened in the last 100 years, right? So I'll start off with giving you a flavor of how some of the most radical ideas in cosmology got started and how they've reshaped our notion, our conceptions of cosmos, our place in the grand scheme of things. So one of the first representations of the night sky that has survived as an artifact is the Nebra sky disk. It's a copper disk, and it's dated to about 2000 to 1600 BC. It was excavated from the Saxony-Anhalt region in Germany. It has the sun, the crescent moon, and the star cluster Pleiades. Why they recorded this, we have no idea. I mean, the only thing we know and that we can surmise is probably ever since Homo sapiens, were able to stand erect, we probably were able to look at the night sky, and we're trying to make sense of this daily cosmic opera of night and day and seasons. So we have no idea why they recorded it, right? But there it is. It's very interesting, and I cite this as an example of an interest, if we can call it that, early data taking, right, of sort of mapping the universe. The next artifact that I have is one of my favorite civilizations, which is the Mesopotamian civilization. And this is the Venus sky tablet, and what this has in cuneiform, so this is a script that has been deciphered, and this marks the positions of the planet Venus on the night sky. So at this point, your jaws should drop, because the Mesopotamians already did know the difference between a star and a planet. So they knew that planets are not producing their own light. It's staggeringly awesome, right, that they figured that out. So let's jump forward to another. So I'm also obsessed with maps in general, and this is one of my favorite maps for a good reason. So this again is data, right? This is starting to take data and looking for, perhaps, this is of course speculation, order in that data, right? Is there a repetition? Is there periodicity? And we think that ancient peoples were preoccupied with that. So remember, this is all pre-science, right? Pre our understanding of an organized way of looking at data, patterns, and ferreting out laws and principles. So this map of the night sky, the Catalan Atlas, we've jumped forward to 1375 AD, is remarkable because before this time, every map of the night sky, so remember at this point, we did not know about anything other than the solar system, right? Our entire universe was a solar system. And it was a time when the universe was geocentric. So the notion, that was the Ptolemaic old Greek idea that the Earth was at the center of the solar system. Well, it wasn't called the solar system then. So what is remarkable about this map is the fact that instead of having a deity, some kind of wise old man representing God with a beard and so on, that would appear in all of these pictures, to denote the divine origin of the universe, this is the first time, an instrument, the astrolabe. So you have these angels sitting at the corners, they're holding an astrolabe. So this is my speculation that this is one of the first maps where we see instrumentation, an instrument and data, and therefore the primacy of the use of instruments, the sort of collision of ideas and instruments to find patterns and laws, right? So let's jump forward to the 1500s. Once, as you all know, something pretty dramatic happened. And that is Copernicus reordering the solar system, also then our universe in 1543, and he moved the pivot from the Earth to the sun. However, this radical idea took a long time to get accepted. Okay? And so, for example, here's another favorite map of mine, which is by Bartolomeu Viejo, who is a Portuguese explorer. And he again has, this is 1568, so after Copernicus, and still.
You can continue.
Okay. And you still see like a geocentric universe. So eventually, of course, we know that data was able to confirm that this is the correct view. Should I hold it in my hand? Okay. This is the correct view of our solar system and the nearby universe. So then we jump forward to moving across scales from the solar system to the Milky Way, right? And so this is an old plate that was annotated by Edwin Hubble in 1924, in which he marks a bunch of Cepheid stars, these variable stars, in the Andromeda galaxy, and shows that the distance to this galaxy, that it is no longer part of the Milky Way. So at this point, we knew about the Milky Way. We knew about our galaxy. So we had moved out of the solar system to our galaxy, right? But he was able to show, he kind of reordered the universe, if you will, because he was able to show this is an external galaxy which is very far away, distinct from the Milky Way, right? So now the universe was opened up. You're beyond the Milky Way to one other galaxy. And then, of course, by now, we're just jumping forward to modern times. And what we see now is this is a blank patch of sky that the Hubble Space Telescope pointed at for a very, very deep look. It was supposed to be a blank bit of sky with nothing, right? And notice what all has shown up. You have like a huge ecosystem of galaxies of various kinds, just littered with galaxies. And then in 1929, he did something even more remarkable. This is the same astronomer, Edwin Hubble. So now that he had blown apart this notion of a singular galaxy, there were multiple galaxies, he was able to chart the motions of nearby galaxies. So this is a plot of the velocity of these galaxies away from us, speeding away from us, versus their distance. And so as you go further and further away, they are hurtling away faster and faster. So this laid the foundation for making the claim that our universe was expanding. Right? So all galaxies other than Andromeda anomalously is falling towards us. Everything else is moving apart. So this means that the universe is now not only replete with many other galaxies, but it's actually expanding. So then we started putting this picture together of the universe, where you have the very early universe. The start is referred to as the Big Bang, a period of very rapid, enormous exponential expansion of the universe. No matter is there at that point, right? So there is no matter at this epoch, there's energy, and we believe that the expansion was actually exceeded the speed of light at that point, right? But remember, once you have matter, you cannot exceed the speed of light. So then you eventually start to assemble matter and eventually form stars and galaxies, and the entire set of cosmic phenomena, galaxies, superclusters, and clusters of galaxies that we now see in the night sky. So this is our current view of the universe, which is just reordering. So what is interesting here, this is different from what I showed you before, is that we also have pegged the timeline of how long we think. Oh my God, what happened? Sorry? Okay. It's okay? Okay. And so what we know now is that there is a very specific era where we can talk about the development of stars, galaxies, and planets. And there's an epoch when you form the first stars. The reason I want you to pay attention to this is the epoch that James Webb is now giving us access to. We're actually getting direct light, photons, from this epoch of the universe, which we did not before. Okay? And what else do we know? We actually know, oh, so I forgot to mention here, that one other important ingredient that was discovered as late as 1998, right, was the fact that not only is our universe expanding, but the expansion is accelerating. And you all know what that means, right? In order to accelerate a car, you need to step on the gas pedal and you burn a lot of fuel when you accelerate a car. So you need some energy, you need an extra source of energy to accelerate. So in the universe, we don't know what is driving this accelerated expansion, but we refer to this quantity as dark energy. And notice this discovery, this enormously impactful discovery, 1998, so not that long ago, right? So the last 100 years have been incredibly rich. So let's come back and revisit now, and now we have really pegged down the timeline for the universe. We know that the universe today is roughly 13.8 billion years old, and we know the first stars formed when likely the universe was between 200 to 300 million years old, and so on. So we know the sequence. We also know what drives the changes and the evolution that we see in the universe. And one of the things that we know is that dark matter, a kind of matter that dominates the mass inventory of the universe, is what is driving all the action. Okay? And we'll see in a minute what I mean by driving all the action. So we also know this inventory of the universe very, very accurately. Okay? So this is the entire energy density of the universe today. Most of the energy density, the bulk, about 70% or so, is this mysterious thing called dark energy. And I say it's mysterious because we know what it does. As I told you, it causes the accelerating expansion of the universe. We don't know what it is. So we know how it manifests, but we don't know what it is. We don't know its true nature. Similarly, when we look at the slice of the pizza that is contributed by actual matter, so that's atoms, everything that we are made of, everything in the periodic table, just 5%. Everything that we know, right? And the rest of the matter, there is more matter in the universe besides just these ordinary atoms that we are familiar with, and that is dark matter. This, again, we believe is a kind of particle that has mass, that formed very early on in the universe and dominates the matter budget of the universe. And it interacts, and we also think it has very peculiar properties, that it interacts only gravitationally. So it doesn't have charge, for example. So there's no Coulombic interactions. And on top of that, it has a weird nature. It is actually collisionless. So how many of you have studied Boyle's law already? Not everybody, but okay. So Boyle's law tells you that for a gas that is made of ordinary atoms, there's a relationship between the pressure, the temperature, and the density. And that relationship is called Boyle's law, and it's called the equation of state. Okay, that describes the properties of the gas. The equation of state, by the same kind of idea, for dark matter is P equals 0, no pressure. So that tells you that whatever this dark matter particle is, it doesn't actually collide. They don't collide with each other. They're collisionless. And somehow all they do is aggregate due to gravity. It's the only force they feel because they have mass. They do not collide. So it's a very peculiar kind of particle, but thankfully for us, the standard model of particle physics that gives you the full zoo of all particles that are possible in the universe has a lot of candidates that would fulfill those requirements. So today, I want to focus on sort of two radical ideas, as I mentioned. One is dark matter, and the other is black holes. And I want to lead you through where and how we have arrived at our current understanding and the newest insights from the James Webb Space Telescope. So first, let me motivate how dark matter was discovered to give you a sort of a feeling for what it really does. Remember, like dark energy with dark matter as well, we know what it does, we know how it manifests, it has gravity. but we don't know what it is, right? So let's jump back to the solar system. So you have the sun, which is the largest gravitating body in the solar system, and all the planets are lined up. And I went to school when Pluto was still a planet and wasn't a dwarf planet, and I'm kind of a holdout, so I still have Pluto in there. I'm not able to give it up. So if you plot, this is called a rotation curve, and this on the y-axis is the orbital speed with which the planet is moving around the sun, and this is the distance from the sun. So notice Mercury, that is the closest in, is moving really fast, and then things slow down as you go further and further out. And the reason this is slowing down, as you all know, that the most massive gravitating body is the sun. As you go further and further away from the sun, the force of the gravitational force falls off as 1 over r squared. And remember, for those of you who've learned enough physics to know and understand this term, all the planets in the solar system are basically like test particles. Okay, we can think of them as test particles that are just sampling the gravity, the dominant gravity of the sun. So this is what the curve looks like, right? So kind of take a good look and see what the shape looks like. So what you can infer from this curve is the most massive object, right? We are measuring distances from the most massive object that is the gravitational force in the solar system, the sun. So the astronomer Vera Rubin and Kent Ford in the 1970s said, aha, let's do something interesting. Let's actually move out to other galaxies, say a spiral galaxy, and let's play the same game. Let's try to measure the speeds of stars from the center outward, right? And see what the curve looks like. So it turns out that you expect it to look like the red curve because you have lots of stars that are piled up in the center, but then they're extended, they go all the way out, and then they kind of peter out, right? So there are stars here, but they're very faint. This picture doesn't capture them. Why is it shorting every? Is it something with the pointer? This connector is working. Oh, this one is loose. Yeah, okay. Change, okay. Okay, so what she measured was actually the white curve. It's almost like there's some matter well beyond where you see the light, which is literally holding up the galaxy, right? So, and this is, of course, very, very different from the solar system. So this is one of the galaxies that she got the data for. They sat for 4 years when they got this data before publishing it. First of all, it was like an unseen entity, right? And in the past, all unseen entities were just like a bookkeeping for our ignorance, right? So remember, there was ether was a concept. People believed because sound needs a medium to travel, they thought, oh, light also needs a medium to travel, and there has to be ether, and that was debunked in the late 1800s. So they were really cautious. There was phlogiston. There were all these, during medieval times, there were all these, invisible fluids. Basically, we were ignorant. We didn't know what they were, right? So they were very careful. They're like, oh, this is a very uncomfortable claim to make that there is something invisible that's sitting there. It's almost like you don't know what's going on, so let's just call it dark matter and make it invisible. But then eventually they measured it, and they measured it in multiple galaxies. So there's a plot from their paper. And so it's no longer a peculiar property of one galaxy. So this seems to be a generic feature of all galaxies. So if you now compare the rotation curve of this planets in the solar system with that of the galaxies, you can see they're fundamentally different mass distributions. So this is telling you that there is a very distributed, extended mass distribution here for a galaxy. And it's going well beyond the light. It's sort of stretching. And you might say, how do they measure it? Well, there's gas and dust that actually extends beyond where the stars end, right? So, and there doesn't appear to be like an edge to a galaxy. It doesn't kind of drop off, right? Whereas the solar system, things really start to slope off. So basically, this is one of the strongest pieces of evidence for the existence of dark matter, that there is an extended distribution of gravitating matter around each and every galaxy in the universe. And incidentally, so every galaxy, including the Milky Way, has what we call a dark matter halo. The other compelling piece of evidence for dark matter comes from the bending of light. And so this comes out of a fundamental reformulation of Newton's theory of gravity by Einstein. So Einstein completely reconceptualized gravity. One of the problems with Newton's theory of gravitation, it works really well within our realm of experience, but it was always problematic to understand how these two masses, the force of gravity is m1 times m2 divided by r squared. How do m1 and m2 know about each other, right? I mean, is there an instantaneous signal? They know how far away they are? You can't have anything going faster than the speed of light, right? So it was always problematic to understand how these masses actually knew about each other, if you will. So what Einstein did was extremely radical. He said, okay, he reconceptualized gravity and said gravity comes out of the interplay between the shape of space and matter. Okay, and that interplay is what gravity is. So he then referred to the entire universe as space-time, a four-dimensional sheet, right? So there's nothing above it. The entire universe is four-dimensional. And I know those of you who've seen the movie Interstellar, remember the Tesseract? Remember falling through the Tesseract? That is a kind of visualization of four dimensions. I can't draw it here, right? This is like a two-dimensional rendering, sort of a schematic, if you will. So you can think of the entire universe as a sheet. There's nothing above, there's nothing below. We all live on this four-dimensional sheet. And it's called space-time because to describe anything that happens in the universe, you need to provide four coordinates. Not just the three spatial coordinates, x, y, and z, but also time. Because it takes light a finite, although it's a pretty high speed, it takes time for light to travel these very large cosmic distances. So you have to know when an event happened as well to describe it fully. So what Einstein realized, he had used mathematics to get this enormous geometrical intuition, right? And he was able to show that the presence of matter, any matter, would cause a little pothole in the fabric of space-time. So it caused a divot or a little pothole. So that every bit of matter in the universe would cause that little pothole. The bigger the mass was, the more extended the mass was, the deeper the pothole. And remember, that is the universe. So light would have to travel. So light from distant objects that actually arrives at us would actually encounter each and every pothole before it reaches us, right? And that information of having encountered a pothole is retained in the light, as we'll just show you. So light carries the imprint of having gone up and down every little pothole in the universe. Of course, the bigger, as I told you, the bigger the mass distribution, the more extended the mass distribution, the deeper the pothole. So here, the schematic shows you have a distant galaxy. We are here on Earth. And this is space-time shown in between. And what you see as little these are galaxies. These are about 1,000 galaxies. They are referred to as a cluster of galaxies. They're held together by the unseen gravity of dark matter. You don't see the dark matter here, but it's there. It's causing a pretty deep pothole here. And therefore, light from this galaxy, when it reaches us, gets, as I said, it goes up and down potholes, and it gets distorted, bent. And so the effect is that we no longer see this galaxy with its original birth shape. We see a mangled, distorted shape. But it's systematic because we can actually track these rays and we can work out what the original undistorted shape of galaxies is. So this phenomenon is called gravitational lensing. And so this is just to flash to you you should go and check this out. This is how Einstein became a sensation overnight, because this is something his theory predicted, and it was tested within a few years of his proposing it. And the context in which it was tested was during a solar eclipse, where the sun, the earth, and the moon all line up. So you can imagine now the pothole is pretty big along here, right? And there's a little pothole from the moon. And you have stars that lie beyond the sun when it's configured during a solar eclipse. And so you actually see the position of these pair of stars to be here because of the bending of light. Whereas once the solar eclipse is over and the sun is moved away, you can look at the same patch of sky and you find those two stars are actually here. So they are a lot closer. They appear to be much further out. So this displacement is what this angle, this deflection, is what Einstein's theory predicts. And so they tested his theory. It was valid. And so that's why he's a household name, because one of the predictions were verified within 5 years of his having proposed it. He proposed them in 1915. By 1919, by 1920, the solar eclipse expeditions had measured the predicted deflection. So we come back to lensing now of galaxies. So let's move out. So I showed you there's a distant galaxy. And so this is the distorted shape of a distant galaxy. So a lot of the early work that I did was trying to develop this formalism to undo the distortion, to see what the undistorted shape looks like, and in the process work out the mass that caused the distortion, the pothole, the depth of the pothole, if you will, how massive the galaxy is that is in between us and this galaxy in this particular case. So this is a Hubble Space Telescope image of a highly distorted galaxy. And what you effectively have is this configuration. You have a distant blue galaxy. It's not a very dramatic galaxy at all. Its birth shape is pretty irregular, lots of stars. And then you have an intervening lens, gravitational lens, matter distribution of a galaxy and its dark matter halo that you don't see that causes this mangling. And this is what we end up seeing projected on the sky. So to separate these out and to back out how much matter you have here in this galaxy is what a lot of people like me do, which is trying to undo the distortion produced by gravitational lensing. So here is, so many of you, is there a problem there? Okay. So the clusters of galaxies, these yellow galaxies that you see, once again, are about 1,000 galaxies that are held together by the gravity of matter. And incidentally, Shomak here works on clusters and superclusters of galaxies. So I urge you to go take a look at some of his recent work discovering a supercluster of galaxies, which is the next biggest state of aggregation of these galaxies. So as I said, there's about 1,000 galaxies. There's a lot of dark matter that I don't show you here. And remember, this object is acting as a lens, right? So it's causing the distortion. And just as many of you are wearing glasses and you have your lenses are calibrated, this is the calibration of the lens. And exactly like the optics of your glasses, these objects that have mass behave like magnifying glasses to the universe. So when you look through one of these clusters of galaxies, you're actually magnifying a piece of the universe, okay? And so you bring into view things that are so faint that if you didn't have this magnifying glass, you wouldn't see them, right? So that's one of the utility of these gravitational lenses. So there's another phenomenon with gravitational lensing that happens. So if you think of light as a tube and you think of light traversing these portals, hey guys, could you cut it out and not talk to each other? So you have light as a tube, and when it hits a deep pothole, it actually splits. And it splits into 3 or 5, and what you end up having are 5 images of the same object. So in reality, there's only one galaxy, but you see 5 images of it. So do you want to tell me where the 5th one is? I have marked 4 of them. Where do you think the 5th image is here? One of you guys who was chattering there. Want to take a shot? The kid in the green shirt. Where do you think the 5th image is here? I'm talking to you. Huh? Can you take a shot? Where do you think the 5th image is? There are 5 images. I've marked 4 of them. Where's the 5th one? Can you tell? It should look similar. Anyone else wants to take a shot? Okay. Punya, do you want to take a shot? Here? That one. Yeah. It's this one. This is just to make sure that you're all alert, and also you can become experts in lensing now. So basically, instead, in reality, there's only one galaxy that is actually shaped like a bicycle wheel, right? That's the real shape of the galaxy, original shape of the galaxy. It gets distorted, and you see 5 copies of it. How do we know there are 5 copies of the same galaxy? Anyone wants to take a shot? That's true, but what is that thing called? Yeah? No, the reasoning is correct. That the potholes are just, Essentially, all objects in the universe have a cosmic fingerprint. What's it called? Exactly, the spectrum. So they have identical spectra. These 5 objects have absolutely identical spectrum. And the probability of that happening in the universe is completely minuscule. And as many of you pointed out and have learned lensing, when you go back and deproject the shape, all these 5 things lead to the same one object. They converge behind the cluster into one location, right? So you actually know that there's only one object. Okay, so let's look at this cluster of galaxies. And so by eye, this is again a Hubble Space Telescope image. By eye, you can all pick out the number of lensed objects, right, that are behind this cluster. So where are the 2 big lumps of matter? Because you remember, matter is causing this lensing, right? So there should be tangential arcs, things that are shaped like huge distorted arcs around wherever you have a huge lump of mass. You can definitely see one here right away, right? Where's the second one? Exactly. So you can already see by eye what I'm going to show you next, which is a map of the dark matter. So this is a map of the dark matter in that region, which is now plotted as a contour topographical cartographic map. So remember, this is that second peak that you saw, the smaller peak, and this is the big peak in the center. So these peaks tell you that dark matter is actually clumped. So these peaks refer to clumps of dark matter. Remember, dark matter, I told you, aggregates only due to gravity. Yep. Gravity, it doesn't clump, it just aggregates due to gravity. Yeah, no, but it'll eventually come back if the force of gravity is strong enough and the density is high enough. No, that it'll get held. No, it will lose its kinetic energy because it will aggregate due to the high density, and it will flip around. It'll have a little bit of kinetic energy. It won't be static. So these things are all moving around. Remember, you also saw the rotation velocity. So things have a velocity, but they do get bound to each other. Okay, so it's a minimum energy configuration for these. These are called subhalos, and the big thing is called the halo. And so you end up with a distribution. So this is a rendering. Let me show you in a simulation what this really looks like when we try to simulate how the universe actually assembled. So this kind of map is a pretty accurate map of dark matter. It was one of the first maps of dark matter that were produced. And you might say, okay, what does it really look like? What does it really mean, right? So that's a rendition in a cartographic way. So it turns out what you really see with the Hubble Space Telescope image is something like this. So patch of sky, so this is the cluster of galaxies, and you are seeing all the distorted arcs that you see, the elongated bits, are things behind the cluster, right, that are getting lensed. In blue, rendered over it, is the dark matter, inferred dark matter. So you can see right away that it kind of follows the light, kinda, right? We don't know how well. That's a matter of active research and debate. We think by and large, dark matter follows light, right? And the reason for that, we'll see in a minute, because we believe the way galaxies form is that dark matter actually flows, aggregates due to gravity, and then ordinary atoms, which is what you need to form galaxies and stars, they're called baryons, they then fall into those they get attracted to those potential wells, and and that's how you form the galaxy. Okay? So this is a hot new result. So this is an image from James Webb, this cluster of galaxies, all these white patches, these are the galaxies in the cluster. And this was the first image that was released. I don't know how many of you probably saw this. This was released by the American president, President Biden in the White House as the first kind of flagship image of James Webb to show that it was working well. So this is extremely dramatic. You see 10 times more lensing than you were able to see with the Hubble Space Telescope. So that will tell you already that you can map the dark matter much more finely, if you will, about how it's aggregating, how it's spatially distributed. So this is, again, as I showed you before, the dark matter that you don't actually see. This is zooming in the inner part of this cluster. So this is a paper that my research group and one of my graduate students is really writing up right now. This is a rendering of the same dark matter distribution in this cluster. Even visually, you can see we are able to make a much finer map. It actually looks much better on my screen than it is rendering on the overhead projector here. So this is allowing us, you might say, okay, great. What are we going to learn by just mapping dark matter? I'll just show you in a minute. So then, what else has JBRA WST found that is super exciting? So it is detecting a lot of faint galaxies that we expected that it would. And the reason is I showed you that James Webb, with its detectors that are tuned to operate in the infrared range of the spectrum, of the electromagnetic spectrum, that's between 1 and 30-ish microns. That is the wavelength at which it can detect. So these are objects that are so far away, in which stars are forming, and it's emitting ultraviolet light. But because the universe is expanding, and as light reaches us, you remember it stretches out, and that's called redshift. So it stretches out, and it becomes longer and longer wavelengths, and we see it in the infrared. And before James Webb, we did not have a telescope that had that range of those specifications and sensitivity to pick up the infrared. So we are starting to see these little specks of assembling the first building blocks of the first galaxies that formed in the universe. Okay, so what is the theoretical construct, context of what's going on? So this is a simulation. This is simulating a universe in the box. This is actually dark matter. And this goes to your question of, how is the stuff assembling? So this is a large computation that shows you of a patch of the universe. All the little blobs that you see are dark matter. And you can see they are aggregating just via gravity. There is no other force. Okay? And this is in the backdrop of an expanding universe with dark energy, with all the ingredients that we know, and a lot of the physics that we think we understand now about galaxy formation. So this is what happens in the universe with the dark matter. Let me just go back and replay the movie one more time. And once this structure forms, in these nodes, right, these regions where these filaments are intersecting and you're assembling huge density of dark matter, ordinary atoms and gas will fall in and then trigger the formation of a galaxy in that region. That's how we believe galaxies form. Okay? So you should check out this web page and this project. There's a lot of publicly available data that you can download and play with for this simulation called Illustris TNG. It's one of the state-of-the-art simulations. So you might ask, okay, what is all of this in service of? Why are we doing this? We are doing this because, as I've told you, we don't know the nature of dark matter. We don't know what particle it's made of, right? And so here are simulations of a patch of the universe. Once again, this is all dark matter. I know we just mock it up to look like light because if we keep it dark, well, you won't be able to see anything, right? So these are two different particle physics candidates for what dark matter can be. One is this cold dark matter, this collisionless weird fluid that we think it is. I told you that's the dominant theory. And this is a particle that is called a warm dark matter particle. Notice this is not as clumpy as this. So if we are able to make a map of dark matter at very high resolution and detail, then we can compare this with the simulation and say, well, does it look more like this or does it look more like this? So the bottom line is, at the moment, all the data is looking very much like this collisionless cold dark matter. The only problem is that there are direct detection experiments. People are trying to find these dark matter particles. We've not found them yet. After 30 years of looking, we've not found them. Okay? And this theory, the cold dark matter theory for structure formation, that's the kind of the standard story that we believe in. There are some tensions that are emerging. Not all observations are in great agreement. It's been enormously successful, don't get me wrong, right? But there are some little, perhaps, cracks that are showing up, which is very exciting. Because remember, cracks can be one of two things, right? Cracks can show you that there's an aspect of the theory that you don't understand that needs to be refined. Your understanding is lacking and it needs to be refined. Or it can point the way to a brand new theory. So we never know which situation you're in, right? So we've got to press ahead And we've got to do studies like this to see how we can confront the observational data with theoretical predictions and see what the gaps are. So at least for me, that's what I find most exciting, because there's so much data now that you can do more detailed tests and comparisons than we could ever do before. Okay, let's now move on to black holes. Okay, so that's the status of dark matter. That's where we are with dark matter, even with James Webb, right? And there'll be a lot more data. Remember, James Webb has just been giving data to us, sending us data for the last year and a half or so, right? There's much to come, and it's performing beautifully. Okay, so what is a black hole? So I think black holes are the most enigmatic objects, and I've sort of been in love with black holes since I was a little kid. And you can think of black holes in 3 different ways. There are 3 different ways to describe these weird objects in the universe. You can think of them as objects, but in fact, what they really are, because I've already told you about Einstein's theory of general relativity and space-time and all of that, black hole is actually a place rather than a thing. However, it is sometimes useful for us to think of it as a thing. So we will move back and forth as it suits us. So one definition for a black hole is every star, massive star in the universe that's about a birth mass of 8 to 10 times the mass of the sun, our sun. When it exhausts all its fuel and then dies with an explosion, it leaves behind a black hole. So it's a stellar corpse. The end state of stars can be a black hole. The other thing is that, remember when we launch satellites, either from Cape Canaveral or Sriharikota, any of the launch sites, or Baikonur, we have a lot of rocket fuel, right? You've seen the rockets. All of you have stayed up. Did all of you stay up to watch the launch of JWST? How many people did? I mean, I did. It was Christmas, but it was late at night here. I was in India. And so anyway, why do we need to give rocket fuel, right? Why do we need to boost it? We have to boost it so that the rocket is released from the grip of Earth's gravity, right? We want to push it out into space. That's what we're doing. And we give it enough fuel so that the escape velocity from Earth's gravity is about 11.2 kilometers per second or something like that, right? So you need to boost it to that speed in order to escape Earth's gravity. So now imagine if you have a gravitationally intensely dense object, extremely dense compact object, a black hole, then the escape velocity from a black hole is actually the speed of light. And I already told you that the speed of light is the cosmic speed limit. Nothing that is material can actually travel at a speed greater than the speed of light, or at the speed of light. So that's why you must have heard people say not even light can escape a black hole. That's what this means technically, right? So now you know the technical reason we say not even light can leave a black hole, and that's why it's called black, right? The third, which now you also understand, is in the context of Einstein's theory of general relativity. Black hole is a puncture in space-time. So let's look at this 4-dimensional space-time. If there was no matter in the universe, it would be flat, right? No potholes, nothing. It would be flat. Now look at what happens when you have the sun sitting, right? So what it does, it makes this pothole. Then you have a neutron star, which is much more dense than the sun, much, much denser. So notice how much deeper the pothole is, right? So the density and the compactness of how the mass is distributed determines how deep a pothole is. A black hole is a puncture in space-time. This is deep, it punctures space-time itself. Don't ask me where the puncture takes you, because we don't actually know. We think it's a singularity that probably takes you to another universe, perhaps, okay? That's speculation. We don't scientifically know it. Okay, so what we are looking at now, so where are the real black holes in the universe, right? So they are at the centers of galaxies. So most, if not all, galaxies seem to harbor a black hole in the center. So we started with a real image of a Hubble Space Telescope image of a black hole. Now this is an artist's rendition. We are going right to the heart of the galaxy, where we believe the black hole is sitting there, and you have gas that is swirling around in red that's shown here. And this black hole is active because it's feeding on the gas. So the gas, what you end up seeing, you see the black hole indirectly because you see the gas that is being gravitationally pulled in, sped up, heated up, and it starts to glow. That's why the stuff is glowing here. So what you see is not the black hole shining on its own, but the material on the way to the black hole that is losing its gravitational binding energy. It's glowing, getting heated up, And you see that. That's how black holes reveal themselves, indirectly. Okay? So then how else do we see black holes? So when black holes, we see them in two states, roughly speaking. They're either fasting or they're feasting. So you have a black hole that is actively accreting, like the little artist's rendition that I just showed you. And those we see as quasars. These are the brightest beacons in the universe. So this black hole that is feeding outshines the galaxy that it's sitting in. Okay, so that's the quasar. We see those. We see those all the way out to the very early universe. In fact, one of the hot results I'm going to show you at the end is a discovery of a quasar by James Webb Space Telescope, a very distant quasar. So then you have these fasting black holes, like the one at the center of the Milky Way. So our own galaxy harbors a black hole in the center that is 4 million times the mass of the sun. Okay, and that is doing nothing. There is not much gas around, so it's not glowing. No gas is glowing. Nothing much is happening, except there's a very little, there's a small amount of gas. There isn't that whole disk that I showed you, the small disk of gas. And we saw proof of that very recently. So I'll show you that. So this is something you might have all seen before. This is evidence for the black hole at the center of the Milky Way. These are orbits of stars around the Milky Way. And this is real data, and those are the years. So this is from the Nobel Prize winner Andrea Getz's research group at UCLA, where they've mapped all these orbits and followed the orbits of the stars. And this tells you, right, from those of you who know the solar system, the orbits are ellipses, right? And so you see these ellipses here, and you know, therefore, at one of the foci has to be the gravitating mass, and the black hole is marked with a star there. That's the location of the black hole. And so how do these black holes feed? You saw that artist's impression of that disk. So this is the cross section from a simulation that one of my students did. So this is the gas disk. Okay, this is the flared gas disk. The black hole is sitting here, and the gas is funneling. So this is the heated gas that is getting funneled in. So how do black holes actually grow? Well, they grow by feeding gas that's right around them, but they also grow by colliding with other black holes. So here are two spiral galaxies. Remember, I'm not showing you the dark matter, right? That's surrounding it. I'm not showing you. This is just the gas and the stars. And you have a black hole in the center that's feeding, so you see it flickering. It's intermittently feeding gas, right? Then these two guys are on a collision course. They're going to collide. We'll see the end state. You'll end up with one really messy galaxy that will take time to settle down. And then you'll see one black hole. These two black holes will also have merged. So this is how black holes grow in the universe. They are born with a birth mass, and then they grow either by swallowing gas and stars right around them, or by colliding. When two galaxies collide, the black holes at the center collide too, and they grow. And so this is, again, showing you the last stage of when the galaxies are colliding. This is the top view. So you have a black hole sitting here, and you have a second one that is going to be plowing and making its way in from the outskirts. So you can see it's slowly winding its way. It's churning up the disk. So this is the disk. It's kind of messing up the disk. This is the side view of the disk. This is the top view that you're seeing. And so this is a simulation that we did several years ago now of a secondary black hole that is making its way in through a gas disk. And so finally, so these, you would see this glowing. It's shown in yellow because this is a process that we might be able to see something in. This donut. Pretty much everybody, right? I mean, it was on every newspaper a few years ago. And so how do we get that donut? So remember I told you that there's a little bit of gas sitting, even though the black hole at the center of the Milky Way is not feeding, a little bit of gas sitting right around it. And there you go, lensing happens again. Here are light rays from the gas that is sitting around. And this is a simulation showing you how you see the donut, right? So This shows you we understand the physics of how we see that shape. And so here are the light rays that are giving us that shape that we see. And these light rays, so you see there's lensing happening. So now you know the two phenomena, right? So you already know lensing, and you see that depending on where the light rays come from, you can make different pieces of this image. You can make the very thin ring or the more detailed, thicker ring. So this explains how you form this image that you see. This is the M87 galaxy. This is the galaxy, the black hole in the center of M87, which is a much more massive galaxy than the Milky Way. This is the Milky Way one that I just showed you right now. And so this one is actually so much smaller, so it would just fit in, right in there. And this is a blow up showing you that, relative to, this is roughly what Mercury's orbit is, sort of the relative size of this donut. Okay, so what is James Webb telling you about the first black holes? Remember, James Webb is allowing you to go very far back in time. And so it's giving us new insights into how the first black holes form. So this is a wonderful piece of data that just came out. And so this is a black hole that formed when the universe was about 600 million years after the Big Bang, so very early on. So this is published. You can take a picture, but you cannot take a picture when I tell you for the next couple, okay? Yeah, just, this is fine. This is a published piece of work. This is not my work. It's from a different group. What I wanted to show you, just wanted to give you a feel for what does astronomical data look like, right? So astronomical data is this, all these dots that you see. Those are the measurements, the photometry, the light that is coming out from this very faint object that James Webb has detected. And so you get the full spectrum, you get the data. So this one, you have both the image photometry as well as the spectrum. So you know the details of where and how far away this object is. And in this case, we are able to estimate the mass of this black hole. So it's a black hole because this spectrum is characteristic of a galaxy that hosts a black hole. And so then what theoretical people like me are interested in is what was the birth mass? This is only 500 million years after the Big Bang, right? So what was happening in the first few 100 million years of this black hole? What was the birth mass? How big was the seed that you started with? So it turns out there are two theories. One is that, as I said, every star ends its life in a corpse or whatever. So that stellar corpse would be, this is the mass of the seed, the initial seed, and this is the final mass you see in the star that is measured in this object, right? So it's estimated in that object. So if you start with a seed that is a stellar corpse, then you have to, so we are looking at growth tracks over time. So this is time. And it would have to grow, if it starts from a very light seed, it would have to grow like this. So in 2005 and 6, with one of my postdocs, we suggested that there has to be another way to make black holes because we were finding some very bright quasars very early on in the universe that were harboring black holes that are 1,000,000 times, billion times the mass of the sun. There's not that much time to grow it, right? Which means there's an easy thing, right? Rather than start from a seed to grow a plant, if you start from a seedling, it'll go, you give it a head start, right? So that's what we suggested. We said these are called direct collapse black holes, and they start life out being more massive, okay? They are about 10 to the 4, 10 to the 5, so 10,000, 100,000 times the mass of the sun and they bypass the formation of the star. So it was a pretty radical idea, and so now that can be tested, and we can see, so this was the idea. So let me show you how the first black holes form. So as I said, the standard way is that you have a star. POP3 just refers to an early star. And you can leave this, it would leave a corpse of about 10 times, maybe 100 times the mass of the sun. That would be the starting mass. And then you would have to grow it, right? So we suggested, well, there have to be some other ways of doing this because that's too small to explain the quasars we see early on in the universe. So we said, well, you could form these direct collapse black holes. And they would start life, with a head start of 10 to the 4, 10 to the 6 times the mass of our sun, or maybe 10 to the 3 times the mass of the sun. So the question is, how does this work? How do these guys form? We think you just have a gas disk, and that gas just collapses. So those of you who've actually sat in a bathtub with water, and then you pull that plug when you're done with your bath, and you see the water going down in a vortex, we think something like that happens in the early universe. So that vortex, you siphon in a lot of water really fast, right? It's a lot of dense flow. And so we think some places in the universe you could get something like that, and that's how you would form these guys. So that's the theory. So of course, we have to make predictions, right? So this was a prediction in 2017. My research group wrote a paper that I led in which, so what you see here in black are what James Webb should see. Okay, this is anything above James Webb, any lines that you see above, that kind of energy emitted by an object should be detectable. Anything below the black points that you see, these are the windows, the filters of on the detectors of JWST. And so this, we made a prediction in 2019, and these orange curves and the purple and the green are the direct collapse black holes. So we said, if you find a black hole very early in the universe, when the universe was 300, 400, 500 million years after the Big Bang, and it was a direct collapse black hole, because remember, black holes could form either way. The telltale sign of a direct collapse black hole is A, it should be detectable by James Webb. It should pop out. It should be well above the detection. This is the limit of detection. Anything below here, as I said, you wouldn't detect. So this would pop up and above, and it would be pretty flat. The shape would be kind of flat. So let me tell you what is special about this idea. So the thing that's special about this idea is that in the nearby universe, like our galaxy, the mass of the black hole is about 10 to the minus 3 times the mass of the stars in the inner part of the galaxy. So there's a correlation, okay, in the masses. And the reason you can see, it's a simple thing in physics, you can see right away, right? Aha, both of these things involve gas. Stars form from gas, black hole feeds gas. So somehow, right, there's a competition for gas, and you end up like this today. But then if you had a heavy seed that forms, direct collapse black hole seed, then there will be a brief period of time in the early universe when the black hole will be bigger than all the stars in that galaxy for a brief period of time. Then it will flip. Because star formation is very efficient, you keep forming stars, you'll end up here. The black hole will be tiny, like in the Milky Way, compared to the rest of the galaxy. So we made these detailed predictions just to show you. So this is a Scientific American article that I wrote called The Puzzle of the First Black Holes. You may want to go and take a look at this one. It explains very nicely. They did beautiful graphics to show you what's the difference between them. So the difference is, if you had a black hole that formed from just the first stars, one of these guys, you actually would not see it at all. You just wouldn't see it. James Webb would not detect those. It depends on how early they would, they could be detected. If it's late in the universe, they have a lot of time for things to grow. But if you're pushing the frontier and looking really far back, you wouldn't find it. You can start from its birth mass to today, or when you detect this object. So this object is called UHZ1, and this is time. And so if you were a tiny seed, you'd have to have a very contrived growth history to get here. Whereas if you start life as a heavy seed, it's pretty straightforward. You just grow steadily and you would reach the mass that we see. So, but what is special about this particular black hole is the fact that we predicted not only should James Webb see it, the Chandra Space Telescope that operates in the X-ray should also see it. It saw it. So that's why this is a super exciting discovery, where we have strong evidence that every prediction we made for every wavelength has to be simultaneously satisfied. So this is the only black hole, quasar, at the moment that has been detected by James Webb and confirmed in the X-ray. So remember I told you that when the gas is being fed really fast, if it's a quasar, it should heat up and glow. That glow will come out in the X-rays as well. And so we are seeing that. So this is definitely a black hole. And what is special about this particular black hole is the way we saw this object was because it was behind a lens. So it was a very faint quasar that got magnified 3 times. That's why we were able to see it. Otherwise, we wouldn't have seen it. So in many ways, as I was telling you when I started, right, that this object kind of brings together like the 2 threads of work that I've been doing for many years, trying to map dark matter out, these magnification maps of these lenses. So remember, these lenses are augmenting, they're nature's telescopes on top of James Webb, right? So we actually found this faint object behind this region that is highly magnified, and that this is a quasar that is only magnified. You don't have multiple copies of it. Okay? So I will just stop here, and I'd be happy to answer any questions any of you have. Thank you. Keep this on. It is traditional to do Q&A, right? Okay, just checking. Yeah, so go ahead. Who wants to ask? Who wants to ask the first question? Yep.
Thank you. Thank you for the beautiful talk. I'm a PhD in biology, so my questions could be very naive, so sorry for that.
That's okay, don't worry about it. No apologies needed for any question, okay? Yeah.
So about the dark matter, the simulation that you showed, so they kind of aggregate together, and that's where the birth of galaxies and stars follow. So to begin with, they were more like spongy thing with like many branches going around. When they aggregate, what happens to the space from where the matter got aggregated?
That's a good question. It gets evacuated. So the initial conditions of our universe, we believe you start with a dark matter field, which is fluctuating. So there are regions, you can think of it like sand piles, right? So there are regions where you have slight sand piles, and then there are regions where you have underdense deficits. So as time goes on, you can see, so here you have, these are the fluctuations where things are piled up, little, overdense piles, sand piles, right? And these are regions where you don't have enough sand, that it's been the sand analogy, right? So what happens when time goes on here is that these regions where you had a deficit become bigger and bigger, and the regions that are peaks get bigger and bigger. So you are changing the landscape from very small fluctuations to amplifying the fluctuations to regions that are overdense compared to the mean, and regions that are underdense compared to the mean. Yep. No, because that's a great question. Because once a region has become overdense above a certain critical threshold, so think of it as, the sand pile has become above a certain height. At that point, that whole region will behave like a little mini universe on its own. And it will separate out, and that is called gravitational collapse. And that region will form a little box in which all the gas that fell into it will be contained in there and will form the galaxy and stars and so on. So that's the reason, that's how you form the Milky Way. So for example, that's the reason that once a galaxy forms, the different parts of the galaxy are not expanding away from each other, because that is like a little mini universe. It's a contained, gravitationally held entity. And the only expansion that's happening is you have one galaxy that forms here, another one that forms here. The space between them is growing. So this by itself is not expanding. Only the distance and accelerating. So this object, technically the word, if most of you want to go Google more and learn, it's separated from the Hubble flow. It becomes a mini universe of its own, and it's a tight box. That's why even though the universe is expanding, right, the distance between New York and Sonipat is not changing. It's fixed. Although the universe is expanding, accelerate, because we are inside a Milky Way, which is the closed box. It's done all its forming, right? And it's settled down in equilibrium, and it's a closed box. Great question. Yep. Need a mic? Yeah. Because I think everyone's curious about your question. Yeah.
Hello.
Yeah.
I'm audible?
Yeah.
So every time an artist tries to show how mass affects space, they'll show something bending. What is that something? Like, so you say space is bending, right? But then what is then the, like we say?
It's matter, the presence of matter. So matter tells space I'm anthropomorphizing
Yeah.
everything, right? Matter tells space how to curve, and space tells matter how to move.
So
That is gravity.
So I think so. So what I'm asking is that when you talk about gravity, people talk about gravitons. So when you talk about space, what is the
No,
fundamental
no,
thing
no, no.
that's
I
making
mean, yeah.
space?
So no, space-time we think could be made of gravitons. So at the moment, we do not have a microscopic theory of gravity, like a theory that combines, just like we do, like if we have a microscopic theory of gases, right? So I know there's oxygen in this room, but I also know how to describe oxygen atoms and molecules and how they disperse and Brownian motion and everything. We do not have such a theory for gravity. It's called the quantum theory of gravity, which has remained elusive so far. So we don't have that kind of description for gravity yet. So people who are working on this field, it's a very mathematical description that people are working with. It's called string theory. So these are approaches to arrive at a quantum description that can be connected to a cosmic level description of gravity. That is not yet available.
Just a clarification. So when I was growing up in school, the way we were taught how galaxies are made, we were not taught about dark matter back then. It was all atomic matter. So are we now saying that galaxies were initially formed by dark matter coming together and that attracted atomic matter?
Yeah, exactly. So the gravitational potential wells of dark matter actually get set up first, a little bit ahead of time, before the baryons slide into the, you can literally think of it, the metaphor as a potential well and things falling in. So ordinary atoms then fall in and they collide. So ordinary atoms collide, right? They dissipate, they collide, they become more condensed, they cool, and they then form stars. They get denser and denser, and they cool, get denser, then you form a star.
So dark matter doesn't directly interact with atomic matter.
Only gravitationally.
Okay.
No, but the frontier, right? So one of the things that many people, including me, are working on is, could there be some other additional way in which dark matter at least interacts with itself beyond gravity? Is there some other little force that we're playing with it, but there is no real evidence that there is such an interaction, let alone the interaction with baryons.
My last question is, you spoke about the birth of a black hole and how it feeds on gases and it grows. Has there been any data about the death of a black hole? You saw it there initially and now it's not there.
So it turns out that can happen in the universe, but the time scale. So the death of a black hole is called black hole evaporation that Hawking came up with. And the time scale, it would take way beyond the age of the universe for an full black hole of the kinds of black holes that I'm talking about. They'll never disappear in not just our lifetime, the universe's lifetime either. So black holes only grow as far as, and that's why we think black holes, actually we can, Hawking and Bekenstein invented this concept of entropy for a black hole because there's an analogy there, thermodynamic analogy for black holes. Lots of cool stuff there, yeah. Yep. Who has the microphone? Is it on?
Yeah, it's on. Yeah, thanks for the nice talk. Yeah, I have two questions actually. The first one is there are many candidates of dark matter available right now. So which one is your favorite? Which one do you think is the most feasible one?
Yeah, so I think, okay, so the most favorite candidate till very recently was called the neutralino. It was a massive particle that formed in the very early universe, and people tailored all their experiments looking for these neutralinos. So the direct detection experiments, they're very challenging. So the experiments basically, they look at inert gases like xenon, whatever, crystal structure of xenon and argon, right? So you have these lattice crystals, and if a dark matter particle went through, it would jiggle that lattice structure, right? Obviously, a truck going on the road could also jiggle. So these experiments were put deep underground in mines and so on, no detection. Well, the rate of a dark matter particle going through the Earth, right, there is uncertainty there. We don't know. Like, we don't know at the distance of the solar system how much dark matter we actually have. But even within the range of rates that we have, it's quite infrequent, but we've not found it yet, after looking for 40 years, okay? So that particle is clearly not quite the answer, unless we have something else wrong. So then what people did in the last 5 years, they moved and they said, oh, there are, as I said, there's a zoo of particles that are available in the standard model of particle physics. They said, aha, there's another particle called an axion. It's a little lighter, but let's go look for it. So they're still looking, no answers yet either, right? So, but we can give them a bit more time. I have to say, given, sort of deeply embedded in this field, looking at the data, looking at the models and everything, to me, it looks like you might have all noticed, I have said there should be one. Why should there be one kind of dark matter? So I am slowly, well, obviously for simplicity, right? Occam's razor, you want as simple an explanation as possible for a complex phenomenon. You try the simplest solution first, which is just one kind of dark matter. It's looking that's not quite working for us. So my personal kind of excitement is about considering two kinds of dark matter that are possibly distributed in different ways and different scales in the universe. So, but that has a lot more free parameters, a lot more freedom in these models, hard to test them. So that's where my personal kind of excitement is at the moment, exploring theoretically those such models and see if we can make some unique predictions that will separate this kind of model, two kinds of dark matter, double dark matter model from a single dark matter model. But it's hard to know. We'll have to wait and see.
A black hole might be a dark matter?
Yes. So we wrote a paper exploring this in great detail a couple of years ago, that you could form black holes. Remember that in inflation era, right after the Big Bang, you could actually form a lot of little black holes at that point. And the question is, what would happen? Could those black holes actually be all of the dark matter that we see today? You could tune that and sort of explain it, but not quite. And the reason, one key problem, as you probably have all figured out, right? Once you put a black hole with even a little bit of gas, it just starts feeding. And if there's a lot of gas, it'll be feeding. We wouldn't know how to stop it. So if these primordial black holes formed so early on in the universe, remember there's a huge amount of time available. They would have grown to monster black holes by today, because we don't know how to stop them. So there are problems with that kind of model of, starting with little primordial black holes being either dark matter or the seeds for all the black holes that we see. So it's not a clean picture, but it's a possibility, and it was worth exploring. So it's explored by the community. There are hundreds of papers, people trying to make the case for that. Any other questions? Yeah. Yeah. It could. So the question is, what happens? So in the center of a galaxy, you have both a black hole and you have dark matter. You have ordinary matter too. And the question is there any way in which they would interact? So we expect that depending on what the candidate of dark matter is, there could be some signatures that could be seen, for example, in gravitational waves that are produced from so gravitational waves are always produced when you depart from spherical symmetry and you have some slight asymmetry. So in the center of a galaxy, because you have the black hole sitting there and you have dark matter piled up, it need not be entirely spherically symmetric. So there could be some distortions and departure from spherical symmetry that could give you some gravitational wave signatures. It's called super radiance. People have calculated it. We have not yet detected it. So potentially detectable. Who knows? But great question.
Okay. Is it evening? Right. Good afternoon, Professor. I'm Sia, and my question is that how exactly do you discover the physical properties of a quasar? Like, quasar? Is it quasar? I'm not sure how to pronounce it. Quasar. I'm so sorry. Okay.
No worries.
So, do you use spectroscopic observations or something? Like, how do you exactly determine that?
Yeah, great question. So how do you actually detect quasars? So you detect them with photometry, so the light that is coming out, as well as the spectra. So what you end up seeing, right, for quasars, typically you detect even the host galaxy, so that you have the light of the host galaxy, and you have the black hole that is sitting in the center, right? So often this would be very, very compact. It would be like a point source. So for example, if you look in the X-rays, so again, it depends on what wavelengths you look at, right? So you can look at X-ray, you can look at optical UV, ultraviolet, or you can look at infrared. So this system will look very different. A quasar in X-rays will look like just a point source. You will not see most of the galaxy. You may see a little bit of fuzz, but you'll see a sharp pointed object right there. Whereas in the optical and UV, you'll see, and again, a very concentrated amount of light coming from the quasar, because the quasar emits in all wavelengths. And you will see the starlight from the galaxies. Depending on the distance, you might be able to separate them out. Because if it's really far away, you cannot, it won't be this clean, right? Because it'll be a tiny blob anyway, and then in the middle. And that's a huge industry for people who are doing image analysis and image decomposition in astronomy, to separate out the quasar from its host galaxy, the parent galaxy sitting around, right? And if you look in the infrared, I just showed you, you'd see a pretty blobby little thing. I mean, you wouldn't see, it's not very distinct, but you actually capture the energy, right? So you get that spectrum, and then you can see how much energy is coming out. And then there are models, because we have these models telling you, when the gas flows in, how it glows, how fast it goes. We can actually predict those spectra that I showed you that we are detecting with James Webb. Yeah, great question.
So, do you think muons might be helpful in this?
Sorry, what would be?
Muons,
Muons.
Yeah.
These are not laboratories where muons are naturally created or emitted, unfortunately. Only photons.
Yeah, so
we don't detect, these objects are so far away that we don't actually detect any direct particles that are emanating from this object.
Okay. So if I'm correct, muons have no actual help in astronomy. They're mainly used in architecture, right?
No, they've been used in nuclear physics.
Okay.
They've been used in nuclear physics, and in the nuclear physics, trying to understand the composition of space plasmas, where they may exist and they may be produced, and in particular in cosmic ray showers. So these are cosmic ray showers whose origin we don't understand, but they produce cascades of particles.
Thank you so much for your help.
Yeah.
I'm Aditya, so I'm a second year physics student here. Great talk. There are lots of questions I had on every slide. And I'm like a small thing. I'm a really big fan of having the perfect kinds of simulations in a talk so that people get the picture correct. So very great simulations. The first question I had was you talked about the seed.
I should come here.
The seeds of black hole, like the seed mechanism of formation of black holes.
Yeah.
And maybe I didn't catch that completely. So you said initially in the the very early stages of the universe, you have these seeds which eventually sort of grow and become into the supermassive black holes.
Yeah.
So if you explained it, I didn't get the part where how do you have so much mass collected in the first place at such an early time in the universe? So how does that happen?
So as I said, you can form seeds in two different ways. So you can form seeds from the first stars that leave behind a little black hole. Those are called the light seeds. And then they would just keep growing, because this would be in the center of a galaxy with lots of gas before the stars formed, other stars formed. So it would just be gobbling the gas and maybe stars, and it would grow. The other mechanism where you form these direct collapse black holes, basically a black hole is a very, very dense object. So basically, if there is another way to bring a lot of gas down to a very small region, and you form a very massive black hole, 100,000 times the mass of the sun, that's a heavy seed, then that too would grow with gas and stars. So all black holes will grow either by feeding gas and stars, that is referred to as accretion, or by collisions with other black holes. And the collisions with other black holes occurs when two galaxies collide, and they both have central black holes in them, as you saw in that simulation.
Right. Just another question.
Yeah.
So we have been hearing about recently that gravitational wave astronomy is the new frontier for doing astronomical research. And off the top of your head, what new frontier will the study of gravitational waves and how they affect space-time? What kinds of inferences could we make from this kind of a study that you can't do with light, say,
Yeah.
that we have been doing for the past 50, 60 years?
Right. So gravitational waves, unlike the electromagnetic window, are a completely new window into the universe. And you've probably all heard about LIGO, right? I mean, India joined advanced LIGO. So these are the collisions of those stellar mass black holes. And these guys are supermassive black holes. Their collision, the gravitational waves that come out, they are actually much lower frequency. They cannot be detected from detectors on the Earth. So basically, like the LIGO arms that you had, you need something like that in space. And there is a mission planned, and it's called LISA. It's going to go up in the 2030s. And so that should detect the collisions of supermassive black holes and the gravitational radiation. So what is really cool about the gravitational waves coming from the collisions of supermassive black holes is that not only because of where they sit, right, the environments, they're sitting where lots of gas stars, when they collide, you will also see fireworks in the electromagnetic component. You'll see some, flashes, electromagnetic flashes that will accompany the gravitational waves. So you can point your telescopes and actually find these coincidences, right? So that's why there's going to be a rich phenomenology that's going to happen when LISA flies. Meanwhile, in a few weeks, we actually am part of this group. I'm also part of the NASA LISA science team that is preparing for, to understand what all we can see and what can we learn. We can learn the masses. Just like LIGO, we will know what the masses of the two black holes were. And then remember, I was telling you in the nearby universe, the mass of the black hole is correlated. We don't know whether that correlation, whether it holds at earlier times, at other times. So we can actually do a really rich amount of astrophysics with what we learn. Meanwhile, right now, we don't have LISA. We have something else. These are called the pulsar timing arrays. There is one in India as well. There's GMRT, so that's part of this array of. So there are pulsars that are basically clocks. They are very precise. They are pulsating neutron stars that are very, very precise, and they are rotating really fast. And if a gravitational wave goes through, you would detect it as a glitch in the pulsar timing. So if you have lots of pulsars, well, pulsars may have their own little glitches, right? Our clocks slow down sometime, whatever, right? But if there's an ensemble of them and they all have a glitch at the same time, then you know a gravitational wave has passed. So at the moment, we have not detected. So you can imagine, right, these pulsars, the gravitational waves, you can either detect them from an object that is merging somewhere, like two black holes that are merging, individual sources, or you can detect a background swoosh of gravitational waves from all the black holes in the universe that are merging.
The equivalent of CMBR.
Equivalent of CMBR. So now there is a first, not detection yet, but evidence for a gravitational wave background. So I'm part of this collaboration called NanoGrav. And our results are coming out. We have some, I can't talk about it. It's coming out end of June. There'll be a press conference. So it's not a detection, I can tell you that, but it's evidence for. So it's not 5 sigma, it's 4 something sigma. Okay. So, but watch out for that result. Yeah. So I think if many of you are looking for areas in astrophysics that you might be interested to go into, I think gravitational wave astronomy, supermassive black holes, and early galaxy formation, right? And the epoch of, it's called the epoch of reionization, when the universe was neutral and then became ionized. There's that period. That's the frontier where the science is, because lots of new data are going to come in. And then the advantage is that we have all of this data from the late universe that you can then correlate with early universe to connect. The idea is to make connections. There's a question there. Yep. Okay. Oh, you've been waiting for a while? Okay, but I think she asked one already, right? So we'll give her a chance first. Yeah. Is it working? Yeah. Not yet. Louder, please. Speak up. Yeah.
Yes, you talked about the potential well that will be created by dark matter, and then baryons and matter will fall into it. But what about the star clusters, stellar clusters?
No, this is before everything forms. This is how a stellar cluster would form in the first place.
Okay.
So this is how the first stars will form, and stellar clusters, nuclear star clusters, globular clusters. This is how everything would form. Yeah.
Thank you.
And there's a sequence. It's the early part of the sequence. Okay, Punya, now you can ask your question.
Okay. Good afternoon, ma'am.
Yeah.
This, this is Panya Chaudhary from Mumbai.
Yeah.
Ma'am, my question is quite intermediate.
Yeah.
But suppose this is a normal small telescope,
Yeah.
and we want to view Pluto.
Yeah. You cannot anyway, but
We cannot?
it's too faint.
Oh.
Small telescope, yeah, not possible.
Okay, then my
you can
question is...
you can probably see Saturn, Jupiter, Mars, Venus. You can't even see Uranus, and definitely cannot see Pluto. Not from a small telescope that you can carry and dismantle and take. No. You have to, if you go to one of the observatories with a dome that has something like 2 meters or something like that diameter, then yes. Even then, it will be pretty unspectacular. Let me just tell you, yeah.
Also, ma'am, you showed a slide where you showed the picture of the Andromeda Nebula,
Yeah.
which Edwin Hubble had discovered.
Yeah.
So, ma'am, was his telescope like a normal size telescope, or was it like huge?
It was 2.5 meters or so. It was very small, but it was the biggest telescope at that time. Now, of course, we have very, very large aperture telescopes, right? But 10-meter diameter telescope. So that was a very small telescope on Mount Wilson Observatory. But at the time, it was the largest telescope.
Ma'am, but to view the Andromeda Nebula completely, wouldn't there be obstructions in the middle? Like,
no, we are not in the, we are the Milky Way, and the Andromeda is an external galaxy to us. That's why we see it as separate. So there's no obstruction because it's the nearest galaxy to us. There's nothing much. There's background stars, but if you look through a small telescope, they are too faint to see. So only this thing will pop up.
Okay.
Have you not looked through a telescope yet? Have you? You have. Okay. Have you seen? I think the easiest. They are going to. Cool. So I think the thing that is very spectacular to look. I don't think there's one coming up soon. Comets. So when I was in high school, they had Halley's Comet. It came through. So that was pretty cool. It was pretty dramatic. You could see the tail. Even with a small telescope, you can see it. Because it came quite close, right?